Hello, everybody. So that video was not Shutterstock. That was actually Neuralink. So that's actual video from the company. So if you want to get a sense for what it's like to work at Neuralink, that video is indicative of the atmosphere of Neuralink. It's an incredibly talented team, and you're going to hear a lot from them tonight. So we're going to actually go quite into depth on what we're doing, why we're doing, how we're doing it, and I'm just incredibly impressed with the caliber of talent at Neuralink. And in fact, the main reason for doing this presentation is recruiting. So we really want to have the best talent in the world come and work at Neuralink. Anyone that's interested in trying to solve this problem, and that's actually the primary purpose for this presentation. So. Okay, so the why of Neuralink, just to go over it, is I think it's important for us to address brain-related diseases. Everyone, if you survive cancer and heart disease, the odds are that you will have some brain-related disorder. So it'll be like Alzheimer's or dementia, and if you don't, friends and family will for sure. And I think unless we have some sort of brain-machine interface that can solve brain ailments of all kinds, whether it's an accident or congenital or any kind of brain-related disorder, or a spinal disorder, if you know somebody who's broken their neck or broken their spine, we can solve that with...
Hey, what's up, guys? This is Elon Musk speaking right now about the Neuralink. If you guys want to comment, like, share, follow, that'd be awesome. My name is Hollywood. I own you, and let's watch this.
How this is possible. But I think there's an incredible amount we can do to solve brain disorders, damage, and all this will occur actually, I think, quite slowly. So I do want to emphasize that it's not going to be like suddenly Neuralink will have this incredible neural lace and start taking over people's brains. Okay, it will take a long time. So and you'll see it coming. So getting FDA approval for implantable or devices of any kind is quite difficult, and this will be a slow process where we will gradually increase the issues that we solve until ultimately we can do a full brain-machine interface, meaning that we can ultimately, this is going to sound pretty weird, but achieve a sort of symbiosis with artificial intelligence. So, but this is not a mandatory thing. This is a thing that you can choose to have if you want. And this is something I think that's going to be really important at a civilization level scale. So, and I've said a lot about AI over the years, but I think even in a benign AI scenario, we will be left behind. And so, and hopefully it is a benign scenario, but I think with a high bandwidth brain-machine interface, I think we can actually go along for the ride. And we can effectively have the option of merging with AI. I think this is extremely important. And if you think about your limbic system and your cortex, your limbic system is kind of your primal needs and wants, and it's like where a lot of your emotions are coming from. And then the cortex is like the thinking, planning part of your brain. And I haven't met anyone who
means they're probably going to try to kill us.
Or the limbic system. So clearly they work together well. Even though your cortex is in principle far smarter than your limbic system, everybody wants to keep the limbic system and their cortex. So hopefully we can have a tertiary layer, which is the kind of a digital superintelligence layer. And in fact, you already have this layer. So it's your phone and your laptop, and the constraint is just how well you interface, the input and output speed. So the output speed is especially slow since most people are typing with thumbs these days. So you have a very slow output speed. Your input speed is much faster due to vision, but the thing that will ultimately constrain our ability to be symbiotic with AI is bandwidth. So in the limit, after solving a bunch of brain-related diseases, there is the existential, it's mitigation of the existential threat of AI, or, yeah, this is the point of it. So creating a well-aligned future, that's the idea.
That's insane. So basically, he's telling us that if we don't compete or come close to AI, that
Composed of nearly 100 billion cells called neurons. Neurons come in many complex shapes, but generally they have a dendritic arbor, a cell body called a soma, and an axon. The neurons of your brain connect to form a large network through axon-dendrite junctions called synapses. At these connection points, neurons communicate with each other using chemical signals called neurotransmitters. Neurotransmitters are released from the end of an axon in response to an electrical spike called an action potential. When a cell receives enough of the right kind of neurotransmitter input, a chain reaction is triggered that causes an action potential to fire, and the neuron to in turn relay messages to its own downstream synapses. Action potentials produce an electric field that spreads from the neuron and can be detected by placing electrodes nearby, allowing recording of the information represented by a neuron.
Whoa. That is insane.
We thought we'd play that twice.
F.
It's so good you have to play
F4F.
it
What's
twice.
that, buddy?
Well, I think like a lot of people in the audience, there's a wide range of knowledge about neurons.
Oh, okay.
I mean, some people view the brain as like this incredibly mystical thing that you cannot interface with the brain, and then some people are aware of deep brain stimulation, such as occurs for Parkinson's patients. So trying to address the broad range of understanding. I mean, neurons, essentially, there's that whole idea, what if we were just a brain in a vat? This is often posed by philosophers, except we are a brain in a vat, and that vat is our skull. Everything that you perceive, feel, hear, think, it's all action potentials. It's all just, it's neural spikes. And it feels so real. It feels very real. But these are all impulses from neurons, what's called a spike. And our goal is to record from and stimulate spikes in neurons and do so in a way that is orders of magnitude more than anything that's been done to date, and safe and good enough that you can, it's not like a major operation. It's sort of equivalent to sort of a LASIK type of thing. So where you can sort of sit down, machine does this thing, and you can walk away within a few hours.
What?
That's it. And
so they were saying this is like an invasive surgery, and he's saying you can just walk in and get this thing, and we're done.
So like there's basically, in terms of key points
Some
that
people say this
are
is
worth
the mark
taking
of the
away,
beast.
the system that we designed in version 1 is capable of on the order of 10,000 electrodes.
Wow.
So each chip, which is 4 by 4 millimeters, is capable of 1,000 electrodes, or has 1,000 electrodes. And we think doing up to 10 is feasible. So this is in contrast to the best FDA-approved system, which is like a Parkinson's deep brain stimulation thing, which would have on the order of 10 electrodes. So the system, even in version 1, that we're going to unveil today, is capable of 1,000 times more electrodes than the best system out there. and they're all read and
they're doing
write.
it today.
So this is really quite, I think, I mean, for something to be 1,000 times more than what is publicly approved.
Bro, we're going to be able to attach this thing to our brain after they release it today.
This will get better with subsequent, subsequent versions. This slide may seem a little generic, because like everything's got robots, electronics, and algorithms at this point, but not threads. So the I feel like I'm in Transcendence.
Nice joke, Elon.
Actually, I was in Transcendence.
This is for pretty much anything. They're going to be able to tap into basically
so
Google
there's
and
very
have
tiny
all
threads
information, and you'd be super,
that
super
are
smart.
about
It'll start
about a
as
tenth,
Alzheimer's, but
roughly,
it'll go for everyone.
of the cross-sectional area of a human hair. So they're extremely tiny threads.
Wow.
In fact, the threads that we have, like I said, even in version 1, are about the same size as a neuron. So if you're going to go stick something in your brain, you want it to not be giant, you want it to be tiny, and to be approximately on par with the things that are already there, the neurons. So this is about the size of a neuron, each thread.
Holy shit.
And then you really need this to be done with a robot, because it's very tiny and it needs to be very precise. So you don't want to pierce a blood vessel. So when so each thread, the robot looks sort of basically through a microscope and inserts each electrode specifically, bypassing any vasculature, any kind of like blood vessel, and making sure that it can be inserted without causing trauma or minimal trauma. Yeah, it's not zero, but
Minimal trauma. What
you won't
the
notice
fuck?
it. That's the important part.
You won't
You
notice
won't like, yeah.
Jesus, Elon, what the fuck is
What
going
real
on?
thing?
I'm ready, though. This could be cool. Would I
so,
do it? Maybe. I don't know.
And yeah, anyways, obviously algorithms. So just to give you a sense of scale, this is how tiny the threads are. That is not even a big finger, that is a small finger. So these threads are just like I said, way smaller than a hair, and there's 1,000 of them. And this is what the robot looks like.
What
it's sort of quite a complex device, but it all comes down to a very tiny point.
Bro, that looks like something out of an alien shit. You know how when you get abducted, right? And they come down and like start cutting. That's what that looks like.
We want to just like,
wow.
you see the robot on the left, and then
That's the needle point? Is that what that is?
what looks like the needles for insertion next to a penny.
Okay.
But in fact, the actual needle that gets inserted is way tinier. It's that little tiny thing at where the arrow is pointing.
Wow.
That's actually the size of the needle. It's about 24 microns in diameter.
Holy shit.
Extremely small. It's so small you can't really even see it in the picture with the penny.
Holy shit. So
And then this is
what
your rain on uranium. No, that's not really. That's agar. So you can get a sense for the robot doing the electrode insertion. That's a very zoomed in view. So they're all very tiny, and the robot is very selectively applying them very delicately, and then this is what the chip looks like.
What the fuck is that?
Action potentials. So each one of those represents one electrode. So there would be up to 10,000 of these of these lines.
So it's
Yeah,
so basically my understanding.
I guess it's always difficult to say. This is going to
like a
be
digital
there's a
mixer,
lot more in
like
this presentation.
neuron, you
So
can put
in terms
like
of things that I think are
100,000
important to bear in
of
mind,
each action,
this
right?
I think
So
has
if
a
you
very
have like
good
1,000
purpose,
neuron,
which is to cure important diseases,
I'm gonna
and
keep
ultimately to help secure humanity's
which makes sense. You can do whatever you
future
want.
as a civilization relative to AI.
Yeah, because we'd be
the
their pets.
threads
if
are very
we don't do
tiny.
it.
And there's a lot of them, and they're very carefully placed. And the operation on a per chip basis, it involves just a 2 millimeter incision, which is dilated to 8 millimeters, and then the chip is placed through that, and then it goes back to being 2 millimeters, and you can basically glue it shut. You don't even need a stitch.
What the fuck?
And then the interface to the chip is wireless. So you have no wires poking out of your head. Very, very important. So it's basically Bluetooth to your phone. Because we'll have to watch the App Store updates for that one. Make sure we don't have a driver issue.
Bro, this reminds me of South Park, the episode where they had the shitter, where Eric Cartman was
But the key is like this is something that
crazy, but it's cool.
is going to be not stressful. Our goal is not stressful to put in. Should work well, hopefully. We'll check it out very carefully before it becomes obviously FDA approved, and it's wireless. So this I think has tremendous potential, and we hope to have this aspirationally in a human patient before the end of next year. So this is not far. And then, as I mentioned earlier, this is the main purpose of this presentation is recruiting, and we need very talented people in all these areas. So it's a lot of very talented people are needed to make this ultimately successful. And then, speaking of talented people, let me hand it over to Max. Yeah.
I need a clicker. Thank you. Thank you. I'm Max Hodak. I'm the president of Neuralink. I remember a couple years ago when we started talking about the idea of Neuralink and that there might be a company and whether this was even a good idea. I remember my first reaction was that I wasn't sure that this actually was a good idea, that the technology was there yet. And I think Elon has this incredible optimism where he'll pierce through these imagined constraints and show you that really a lot more is possible than you really think is today. And you have to be very careful telling him that something's impossible. It better be limited by a law of physics or you're going to end up looking stupid. And so I've wanting to build a neural interface has really been like a central goal of my life for basically as long as I can remember. I think like we talk about AI being potentially the last invention that we have. I think that a high bandwidth BMI might be like really the first invention in many ways of like the next chapter of us. It's just really, like as Elon alluded to earlier, everything about your experience, your thoughts, your memories, it's all in your brain and represented in the firing statistics of action potentials. So, all right, so just what is a BMI? And we'll go through this fairly quickly, I think. So you start with hopefully a brain and a machine.
So it's an interface.
But the machine is just a stand-in for the outside world. It could be another brain, it could be software, it could be a robotic arm. But you want to receive energy from that world and impart through the senses like vision and audition and impart energy back into the world through things like motor control. And that language that they use to communicate, putting aside the interface hardware for a second, it's very important to understand what that is because people ask like, oh, can I talk to my dog or can I do these things? But it's important to understand what that language is. And that language, in the most general sense, is information. To a first approximation, everything is information. But we just consider here the information represented in neurons. And so consider two like toy neurons. One, so these lines are imagined action potentials. And so imagine a neuron that fires very regularly like a metronome. Like this doesn't tell us anything. There's no information conveyed in this signal. We don't learn anything from it. On the opposite end of the spectrum, imagine a neuron that fires completely randomly. This also doesn't tell us anything. This also doesn't carry any information. Now we know that these two degenerate cases are not what neurons do because if you fit a model from recorded neural activity to behavior of things like a cursor of a patient or a subject that's implanted and you correlate these, then you can build a graph that looks like this. And this is a figure from a classic paper in this field, from like the academic heritage of this field from 2003. I think that actually some of the authors of this paper are in the audience today. And you can see it's the x-axis is number of neurons, and the r is the goodness of fit. And you can see that as you add neurons, the quality of the model improves. This tells us that neurons and their spike trains carry information about things. Here it asymptotes fairly quickly. That's because what they were fitting here was just 2D cursor control, which has simple dynamics. And if you have tasks that are more complicated, then you need more neurons. So the classic definition of information is a difference that makes a difference. It's just some piece of information or knowledge that tells you something. It's like a very abstract concept, but it's such, like information theory is such a deep rabbit hole. If you haven't seen it before, the original paper, Mathematical Theory of Communication, is like, it's very readable. I highly recommend it. You'll start seeing information everywhere. It will totally change the way you view the world because the world is information, as we've talked about before. And understanding information also gets this question of, well, why do you have to have an implantable device? Why don't you have EEG or a wearable or an optical thing? And the answer, of course, is like, well, these are different information carriers, and what information are they carrying? And we know that, like, if you open a back issue of the Journal of Neuroscience and you want to understand how some species of bird encodes sound localization or something, you'll find a discussion of spikes. And we, as far as we know, everything that we care about is found in the statistics of spikes. So that's what we focus on. There are other things like fMRI or EEG. These are different information carriers carrying different information, which we believe is impoverished relative to spikes. I think that's the scientific consensus. And so the question for all these different things is, well, what information is found in your carrier? We focus on spikes. That means we have to be inside the brain because there's no ceiling that we're aware of on that with respect to that like grand vision of your perception, your thoughts, everything, like motor output, re-embodying
perception,
lost limbs.
Or quote a thought.
And so why does that mean that you have to be inside the brain? So you want spikes. Well, people have studied if you take a neuron and you put an electrode on that specific neuron, so you have a ground truth electrical potential of that one neuron, and then you place an extracellular electrode nearby, which is what our electrodes in the Utah array and other people are like. We're not in the cell, we're near the cells. And then you measure how far away from a neuron can you be when you know what the ground truth spiking activity is, can you no longer see the spikes? And it turns out that the answer is about 60 microns, which is like 0.06. It's very small. It's a lot less than a millimeter. So you have to be firmly under the skull. Like there's no wearable that is going to get you spikes. This is a physics constraint as far as we're aware. And so now I just want to talk about briefly that Neuralink didn't come out of nowhere. There's a long academic heritage of research here. The cochlear implant has reached millions of patients since the 50s for deaf patients. Over 100,000 patients have received deep brain stimulation for Parkinson's and essential tremor and dystonia and now other indications. And about 20 patients have received the Utah array, which is a little 100 electrode rigid metal silicon device. And even though it has very few channels, they've been able to do some really cool stuff with it. There's videos on YouTube of brain gate patients doing things like controlling tablet computers or even texting each other through Utah arrays just from the small number of electrodes. And so many of the people on the team at Neuralink came from this academic work. I got my start working in a lab at Duke University studying how mappings between brain and like the screen space change. So if you make it so that the joystick goes, like the cursor goes sideways when you push forward instead of up, like how does the brain change that representation? So the point is that there are lots of people that have been looking at this problem from lots of angles for decades, and we're in the greatest sense building on the shoulders of giants here.
I could see that. And
so the question is, why not use one of those devices? Why not use a Utah array or a deep brain stimulator, implanted pulse generator? And in the Utah array case, the rigid sharp metal electrodes produce a fairly strong immune response. And this doesn't end up hurting the patient, but it does mean that you lose the ability to record single spikes over some period of time, usually between 1 and a couple years. There's also a big percutaneous connector through the scalp. So you need to plug in big external electronics, and you're never really confident that the risk of infection is gone for the duration that you have the implant. Deep brain stimulators solve a very different type of problem. They are very effective for some Parkinson's patients, but they have only a couple electrodes, and they're really geared towards injecting large amounts of current, not recording single spikes. So they're really a very different, the DBS is really just a very different type of platform for a very different type of problem. So we had to go back to the drawing board and start over to build something that met the goals that Elon laid out for us. We knew, as Elon mentioned, that whatever we built, we wanted it to be completely wireless. We didn't want any connectors or wires coming through the skin. It had to be something that would last for a long period of time, not something that you'd have to take out at 2, 3, or 4 years in. It had to have practical bandwidth. So we talk about high bandwidth or ultra high bandwidth. Like, what matters is that for the task that you're after, there is practical bandwidth that allows you to effectively do that thing, whether that's cursor control or typing or robotic arm or maybe in the future vision. And it has to be usable at home. It can't be something that you go into a clinic at the hospital for 2 hours a week and under tight supervision of technicians plug you into the amplifiers and turn it on. It has to be something that you can live with.
Oh, that'd be weird.
And so 2.5 years ago, we were nowhere close to any of that. This is a photo of some of the prototypes that we've gone through over that time. So we started on the far left. That's an entirely passive board that has 64 electrodes on it and connects to connectors that go to big external amplifiers. And then we added integrated electronics with our first custom chip. That's also 64 channels. And then there was a big leap to the device that Elon showed a photo of earlier. That has 3,072 electrodes in a fully implantable package with just a USB-C port coming out.
What?
And then we took a step back in channel count because remember we have to optimize safety, longevity, and bandwidth all together. And so in order to optimize some of those other things, we moved to an easier to manufacture system that has 15, 36 channels and a USB-C port. And those last two are the focus of the paper that we released today. And so we've learned a lot from these. We've recorded a lot of data through these. Like these are actually used every day at Neuralink to record neural data and work with it. And they taught us a lot about the architecture that we think was the basis for our first human product that we're calling N1. And the central component of that is the N1 sensor.
Wow.
It's a little hermetic package. It's when it's fully assembled, this is missing an outer mold. It's into an 8 millimeter diameter, 4 millimeter tall cylinder. And each of these has 1024 electrodes, and we can stim and record through every one of those channels. Opening it up a little bit, you can see there's the thin film, which has the threads that Elon talked about, which is the wisp going off to the side. There's a hermetic substrate, and then that gets welded later to a package that goes over top, and that's mated to our custom electronics. And we'll go into more detail. We'll have the technical leaders that work on each of these talk about these in more detail over the rest of this presentation. So yeah, I mean, this is just not to belabor the point. I know that Elon really hammered this in, but these things are very, very small. They're not. You can't manipulate these. This is one photo. This is not two photos joined together, and you really can't manipulate these with your hand. That part at the top is just a backing material that's surgical packaging. They're peeled off. The threads are peeled off that one at a time by the robot to place into the brain. And we had to build a surgical robot. And the first impetus for this is just you have to place these threads. You can't manipulate these threads. You need a robot. And then that grew into understanding where the blood vessels are and imaging into the tissue, and the surface of the brain moves because you're breathing and you have a heartbeat, and there's lots of complexity of dealing with this incredibly high entropy substrate. And it's not all offloaded to the robot. It's the robot's under the supervision of a human neurosurgeon who lays out where the threads are placed, but it would not be, the surgery is not possible without the robot. And so the N1 implant, we can place, as Elon mentioned, many of these, possibly up to 10. In one hemisphere, for our first patients, we're looking at four sensors, 3 in motor areas and 1 in a somatosensory area, which are connected via very small wires tunneled under the scalp to an inductive coil behind the ear. And that connects wirelessly through the skin to a wearable device that we call the Link, which contains a Bluetooth radio and a battery. And this is, importantly, the only battery and radio in the implant. So if you take this off, the implant shuts off. And if there's software upgrades or security issues, it's much easier to upgrade the firmware on the pod than it is to try and change the implant. It'll be controlled through an iPhone app. You won't have to go to a doctor's office and have them have an exotic programmer to configure it. And the first thing that you'll have to do is learn to use it. Like, imagine if you've never had arms, and then suddenly you have an arm, and you have to pick up a glass on the table. It's like not a cognitive task. You just how do you can't think your way through that.
This is going to be
and so it's kind of a trippy experience at the beginning, where like patients at first it just kind of wanders around, and then they figure out how to break the symmetry, and they learn how to control it, and that's like it's a long process. It's like learning to touch type or play piano. And so for the first product. we're really focusing on 3 distinct types of control. The first is giving patients the ability to control their mobile device, because we heard from over and over again from patient groups that if you have to have a caretaker around to press buttons for you, what's the point? You might as well have them do the thing. You have to get self-sufficient using the devices on your own. And then redirect the output from your phone to a keyboard or a mouse on a normal computer. It'll just show up as a Bluetooth mouse or a Bluetooth keyboard, like any keyboard or mouse that you can use on any computer. And as Elon mentioned, this is a forward-looking statement. There's a whole FDA process we have to go through. We haven't done that yet. This is like, these are aspirations. But we are working as hard as we can towards our first in-human clinical study next year. And again, these are plans, but the primary indication for that will be complete paralysis by upper cervical spinal cord injury. And we're expecting that those patients will get 4 10/24 channel sensors, 1 each in primary motor cortex, supplementary motor area, and dorsal premotor cortex, which are 2 motor planning areas, and closed loop feedback into primary somatosensory cortex, which is like when you type or walk or pick up a pen, those aren't visually guided movements. Your body has all these senses of where it is in space and pressure and temperature and lots of other feedback. And we think for really high fluent control, you have to provide that back to the brain for the synthetic effectors also. And of course, fully wireless and able to use it at home. We think that there's a huge difference between something that you get to use 2 hours a week at the hospital versus something that you're living with every day and your brain is adapting to as much as the device is adapting to your brain. And so to bring up the other colleagues, this team is like, I'm incredibly lucky to get to work with this team. We're going to go into a little bit more detail on, we think that decoupling implantation from the electrodes is incredibly important. The reason that you have these issues where things like these like tungsten microwires get rejected is they're stiff and they're stiff and sharp and they tear the brain, and they have to be because they have to get into the brain. And so if you can decouple the process of getting it into the brain from what is left there, where it can be much softer and have material properties like the brain and maybe be coated in things that help the brain recognize it as itself, that's really important. And then the thin film polymer leads, the threads themselves, are really cool material science, and we'll go into more detail on that. And then we'll also talk more about the chips, and then a little bit more on just the neuroscience of how information is represented in firing statistics in your brain. And so with that, I'd like to welcome Dr. Matthew McDougall.
Oh, shit.
Thanks, Max. I'm Dr. Matthew McDougall. I'm head neurosurgeon at Neuralink. When I'm not at Neuralink, I'm a brain and spine surgeon here in San Francisco at CPMC, California Pacific Medical Center.
Okay.
Before that, I was at Stanford, where I worked in labs that implanted and designed advanced brain-computer interfaces. I originally became a neurosurgeon because I wanted to help people live happier, healthier, longer lives.
Yeah, there's that longer part. Yeah.
I've been humbled in practice by how powerless we are to treat many of the most debilitating neurologic diseases. People afflicted with spinal cord injury, schizophrenia, autism, and a host of other neurologic conditions.
That's a good idea.
Have far too few options. I work with Neuralink because we, for the first time in history, have the potential to solve some of these problems. Before we get to how we get the device in, we have to talk about our guiding principle at Neuralink. It's safety. Everything we do at Neuralink is filtered through the question, will this make me more likely to want to get one? Will it make me more likely to recommend this to my family and friends? This approach impacts every design decision we make. So while for the immediate future, Neuralink's devices will only be intended for patients with serious, unmet medical needs, our design philosophy is that this should be safe enough that it can be an elective procedure. So what have we done to try to make it safe?
So
For starters, we've created very small threads. They displace a lot less tissue than the traditional methods. In my regular practice today, I routinely implant large, deep brain stimulator electrodes into the brains of my patients.
Oh,
They're big enough to have about a 1 in 100 chance of causing a significant hemorrhage. They displace and disrupt enough brain tissue that you can often see neurologic consequences just from placing the wire.
Damn.
We can do better than that. Neuralink's threads are so thin that they're difficult to see with the naked eye. They're much smaller than the width of a human hair. They're small enough that a human surgeon can't actually implant them without help. So we created help. Neuralink developed a tool that we're extremely proud of, the robotic inserter. Inspired by designs conceived of in labs here in the Bay at UCSF and Berkeley, we developed this robot that can rapidly and precisely insert hundreds of individual threads representing thousands of distinct electrodes into the cortex in less than an hour. This tool allows a surgeon to aim between the blood vessels that cover the surface of the brain with micron scale precision. The region of the brain shown in this video represents only a few millimeters of surface of the brain. As you can see, the brain's surface moves with the heartbeat and breathing. The robot tracks and adjusts for this movement. Using this tool, we can greatly reduce the risk of harming cortical vessels and causing bleeding. Here, the robot is selecting individual electrode threads and placing them into the brain in the pre-planned location with remarkable accuracy and repeatability. Using this system, we've been able to rapidly place thousands of electrodes into the cortex without causing noticeable bleeding. We also have an in-house histology team that examines brain tissue to help us choose electrode profiles and materials to help us minimize tissue damage. When you think of traditional neurosurgery, you probably think of something very invasive. Traditional surgery on the brain isn't something that patients ever look forward to or are excited about, except in the most dire circumstances. Usually a clamp is attached to the skull to keep it rigidly immobilized to the operating table. We often shave all or most of the patient's hair. Patients can end up with large visible scars. At Neuralink, we want to create an entirely different patient experience, something more like LASIK. No scars, no big scars, no hospital stays, no short procedures, no hospital stays, very short procedures, and of course, in the end, you get to keep all your hair. We even want this to be possible under conscious sedation. That means you can get rid of the complexity and the risk of general anesthesia, as well as many of the unpleasant side effects, nausea, sore throat from a breathing tube. To be absolutely clear, our first clinical trial patients are going to receive an experience much more like traditional neurosurgery. But our aim is to simplify the procedure, down to the injection of local anesthetic, a very small opening in the skin, a painless opening in the skull below, quick and precise placement of threads into the cortex, and then we fill that hole in the skull with the sensor, allowing the scalp to be closed up over it.
What the fuck?
Behind the ear, we'll make a small incision to insert the coil. We will tunnel tiny wires under the scalp to connect the sensors to the coil. That's the process.
How do you tunnel
I believe
the wires
that Neuralink is going to be able to provide us in the medical community with a platform that can finally enable us to treat some of these very difficult to treat diseases, also to understand them better. I hope you find this as exciting as I find it. If you feel you might be able to help us, don't hesitate to contact us.
I am not.
To talk more about the technology behind all this, I'd like to introduce Vanessa Tolosa, director of our Neural Interfaces group.
Yo, how many of you guys in the chat can do this? Let me know if you guys would do this in chat.
Hi, I'm Vanessa Tolosa. I lead the Neural Interface group at Neuralink. Our team consists of engineers and material scientists who are responsible for making the probes that get implanted into tissue, the packaging for the electronics, and integrating these two components together. We also do all the testing and characterization of these parts. Before joining Neuralink, I led a neurotech team at Lawrence Livermore National Lab. There we worked on a wide range of neuroprosthetic technologies that were used both in the academic and clinical settings. I decided to join Neuralink because I saw an opportunity to take all of this exciting work that we were seeing in neurotech research and actually make them accessible to patients at a much faster time rate than what medical device companies have traditionally been able to do. With that in mind, at Neuralink, we set out to create a fully implantable neural interface with thousands of channels that are capable of single spike resolution.
If they could,
This device must last a long time in the body. To do this, it must be small,
one of the people,
flexible, and made of biocompatible materials that will minimize the brain's immune response.
see if they're all
To
fucked up
protect
and
the
shit.
electronics from the caustic environment of the body, it must have airtight packaging, also known as hermetic packaging. The device must also be able to both record from and stimulate neurons. This is essential for a highly functioning BMI.
Yeah, 'cause you
Finally,
need to know
the
everything.
manufacturing process must be scalable and capable of making micrometer-sized features consistently.
What they see, what
Currently,
they
there are
feel.
no research or commercial devices that meet all of our requirements. So we built one out of microfabricated thin film polymers.
Human hair.
Just like in semiconductor chip manufacturing,
God,
we use a
that's
layer-by-layer process that generally consists of 3 repeating steps. We're either always depositing material, patterning a material through photolithography, or etching away a material.
Huh.
Depending on the complexity of the design, these steps could be repeated over 100 times. And to make things more challenging, we are limited to materials that are safe for the body. In our current design, we have a 3-metal layer process that results in a 5-micron thick and 10 to 40 micron wide probe. To give you an idea of how small this is, red blood cells have a diameter of about 8 microns. And an average strand of hair is about 100 microns. Yet in this small footprint, we're able to fit our electrodes, our wires, and the insulation for each of those wires. With
Wait,
microfabrication, we can drive
whole
features
thing?
down to the size of an electron beam. So this is great because we want to make our probes as small as possible. Essentially, we want it to be invisible to the brain.
Yo.
But there are other factors that limit the size of our probes. For example, as we make the wires smaller, it increases the resistance of those wires. And as the resistance increases, it makes it more difficult for us to separate our signals from our noise. Similarly, there are other technical challenges and trade-offs that are related to higher channel counts and manufacturing yield, electrode size, and material and tissue safety. At Neuralink, we have an incredible team that's been tackling these challenges and have been able to make high channel count polymer probes. And this image is a silicon wafer that holds 10 of these arrays, these polymer arrays. In this design, each of those arrays has over 3,000 channels. So what that means is in this one wafer, we've manufactured over 30,000 electrodes and over 30,000 insulated wires. This is something that can't be done with the way current medical devices are being made. That rainbow effect is caused by the small feature sizes on these devices that are interacting with the nanometer size wavelengths of light that are reflecting off of them. If you were to zoom in on the ends of one of these arrays, you'll see this region where we put all of our electrodes. So each of these vertical filaments that end in a loop is what we refer to as a thread. And each of these threads can be placed independently into the brain using our robot during surgery. This design is called Linear Edge. It's one of over 20 designs that we've made for our R&D work. We've progressively been increasing the number of electrodes per thread without significantly increasing the width of each of these threads at the base. We've been able to do this by adding layers and reducing the sizes of the wires down to as small as 350 nanometers. This is less than the wavelength of visible light. Because we're using a lithographic process, essentially if we can draw it, we can also make it. So on one end of our probes are the electrodes. On the other end are where we connect the probes to the electronic package, or to the electronics through conductive feed-throughs. This substrate is part of the hermetic electronics package. Standard methods of connecting the probes to the electronics package usually involve some kind of large plug-in type connector or a polymer-based glue that bonds the two components together. But as we increase density and decrease the footprint, becomes impossible to achieve hermeticity in standard medical device connectors. This is due to several reasons. One of them is how these substrates are currently manufactured. Hermetic feed-throughs consist of holes that have been packed with conductive materials and are embedded in an insulating substrate. As you drill more holes and pack them more tightly together, these brittle substrates, typically made of ceramics, become more susceptible to cracking. Also, as you make the holes smaller, it becomes more difficult to fill them with this conductive material without getting non-hermetic voids. Standard processing also requires exposure to high temperatures, typically over 700 degrees Celsius. At these high temperatures, the coefficient of thermal expansion, or CTE mismatch, between the insulator and the conductor can cause circumferential cracking or interfacial gaps during the cooling phase. We're able to get around these problems by developing a new process. So rather than making the probes and then the substrates and then connecting them together, instead we microfabricate them together into one monolithic component.
Oh, snap.
This provides a tight seal at densities that current methods with standard materials for medical devices can't achieve. So far, we've used this process to make a hermetic thin film substrate with over 1,000 connections over a 2.4 millimeter by 2.4 millimeter footprint. Next, we assemble the electronics and then also attach a wired lid using a laser welding process. These two steps have required a lot of internal development as well. The result is the sensor that's ready for final assembly and implants into the body. Next, you'll hear from my colleague DJ about our custom electronics.
Thank you, Vanessa. My name is DJ Saw, and I'm the Director of Implant Systems at Neuralink. My team focuses on building chips and systems to get neural signals recorded from our electrodes out of the brain, and also to put information into the brain. Before Neuralink, I was at UC Berkeley, where I co-invented NeuralDust, which is a technology to power and communicate with small implantable systems using ultrasound waves. Typical chip lifecycle from design to verification to tape out is approximately 1 to several years. At Neuralink, we had the ability to co-design our chip with the rest of the system, and the tight feedback loop from this organization has enabled our small team of analog and digital chip designers to tape out a new design every 3 months on average. That means over the past 24 months, we've done 8 tape outs in total, representing 15 different chips that have been designed, fabricated, tested, and used in development. Wow. The artwork that you see on the top of the slide is of some of the actual chips that we've made so far. For any custom chips we make, the architecture can vary substantially, but the basic ideas are the same. Neural signals recorded from the electrode typically look like the one on the slide. And in order for us to extract the information that we care about, we need to first amplify, filter, and digitize those neural signals, and use digital logic to process and send out the bits we want for BMI. We also need ways to diagnose any issues with our electrodes and be able to drive stimulation engine to inject charge to the brain when required. Our latest chip is called N1 System on Chip, and it is physically small, measuring only 20 millimeter squares or 4 by 5 millimeters. It is low power, highly configurable, and it has 1,024 simultaneous record and stimulation capable channels.
Holy fuck.
And it has on-chip spike detection. To dive deeper into N1 SoC, I'd like to highlight 3 key innovations, and they are 1, analog pixel, 2, on-chip spike detection, and 3, stimulation on every channel. The first is analog pixel. Before we can convert analog neural signals into digital bits, we need to amplify and filter them. And this is where the analog pixel comes in. we want to have one analog pixel per electrode so that we can configure them independently. So in the case of N1 SoC, there are 1,024 analog pixels. Analog pixels also take up a significant portion of the physical space on the chip,
Bro, they
and how well they work
brainwaves
determines
into
both
the
the signal
matrix.
quality
Do you see this?
and the characteristics of the overall neural interface.
Oh shit! Shit is about to go down.
The goal of
motherfuckers.
analog design
It's about to
is
go down.
analog pixel design is to make it as small as possible so we can fit more, as low power as possible so we generate less heat and have longer battery run times, and as low noise as possible so we get the best signals. Now, the challenge here is that these goals are at odds with each other. For example, we want to achieve lower noise on the amplifier so that more spikes can be detected. But as transistors get smaller, it becomes harder to get lower noise while keeping the power the same or less.
Damn.
Since the start of Neuralink, we've gone through 3 major revisions to the analog pixel, progressively improving both the size and power while maintaining performance. Over the past 24 months, we had 7-fold improvements in the size of the analog pixel, and our latest pixel on the right is at least 5 times smaller than the known state-of-the-art of similar architecture with 1 pixel dedicated per electrode, as published in the academic literature. Second innovation is on-chip spike detection. Once the signals are amplified, they're converted and digitized to zeros and ones by our on-chip analog-to-digital converters.
What the fuck?
As you'll hear in a second, spikes or action potentials shown on this slide are often critical for certain BMI tasks.
Huh.
Currently, there are several different methods for detecting spikes, such as thresholding, or more sophisticated methods such as principal component analysis. At Neuralink, one of the robust ways that we came up with is by directly characterizing the shape, and it's worth noting that this is different than template matching in that it gives us more information in a general way. In certain cases, we can actually identify different neurons from the same electrode based on their shapes. Our analog pixel can capture the entire neural signals sampled at 20,000 samples per second with 10 bits of resolution, resulting in over 200 megabits per second of neural data for each 1,024 channels that we record. In our previous systems that you heard about, we were able to stream this entire broadband signals through a single USB-C connector and cable, and we performed real-time spike detection on an 8-core machine running our optimized C code. Now, we wanted to completely eliminate connectors and cables for N1, so we had to modify our algorithms to fit into the hardware by scaling both, making it both scalable and also low power. And then we were able to also implement this algorithm in our N1 SoC. Our algorithms can compress neural data by more than 200 times, and it only takes 900 nanoseconds to compute, which is faster than the time it takes for the brain to realize it happened. Finally, it was important for us to enable stimulation from every channel that we can record from and make it configurable and high resolution. To make this work, we custom designed stimulation engine for electrical stimulation that can coexist alongside our analog pixels. Our stimulation engine has 0.2 microamp of amplitude resolution and 7.8 microsecond of time resolution. There is a 16:1 ratio of electrode to stimulation engine, so we can't stimulate every channel simultaneously, but we can within each stim pulse, usually in milliseconds, and we can also stimulate any combination of 64 channels at the same time.
Yeah.
So in summary, looking through our N1 SoC, it has 1,024 analog pixels that we can record from simultaneously with 7.2 microvolt RMS noise while only consuming 6.6 microwatt of power. It has on-chip analog to digital converters, on-chip spike detection that can compress neural data more than 200 times, and it only takes 900 nanoseconds to compute. Stimulation engine with 0.2 microamp of amplitude and 7.8 microsecond of time resolution. and finally, diagnostics for electrode and impedance measurement. All of these functionalities that I outlined are integrated into a single 4x5 millimeter silicon die. Next, my colleague Flip will tell you more about what can be done with these signals.
Thanks, DJ. My name is Philip Sabis, and I'm the senior scientist at Neuralink. Before Neuralink, I was at UCSF, where I was a professor of physiology. There, for 16 years, I ran a lab that studied how the brain processes sensory and motor signals. We developed new neurotechnologies, and we studied how to take those tools and use them for neural engineering applications. Today, I'm going to tell you about how it is that we can use those amazing devices that Vanessa and DJ just told you about to communicate with the brain. Now, specifically, I want to tell you about two things. First, I want to show you that the work that we're doing doesn't come out of thin air. We're building on over a century of neuroscience research and decades of neural engineering research. These provide a solid foundation for the sorts of things that we're talking about. Second, I want to show you why we believe that even more advanced applications are possible with more advanced devices. Now, when Elon contacted me over 2.5 years ago now, and told me about his vision for the company, I knew that I wanted to join for these two reasons. Because I knew that the technology was at a point where, with the right team and the right vision, and a long-term vision, we could do the sorts of things that we're talking about. And I knew that with that team, we could do things that no one had even dreamed about yet. Okay. So the first thing I want to show you is a video. Many of you who are seeing this have seen videos like this before, so you know what it is. But if you don't know what this is, I have the distinct pleasure of telling you that right now what you're looking at is the brain at work. This is, in fact, traces of a bunch of electrodes that came off of one of our devices, a bunch of electrodes from a single thread. And each trace shows you the voltage waveform in time as it's coming off of one of those threads. Now, if we focus in on one of those traces, the first thing you may notice is that there are these big voltage deflections that happen periodically, and these are the spikes that Max and Elon and others have talked about. These spikes occur, again, when a neuron has an action potential. And this is the fundamental element of communication within the brain, and this is the thing that we want to tap into. This is what we want to be able to record. Now, as DJ just told you, we have algorithms that can detect these spikes in real time as they're happening. And that allows us to collect data that looks something like this. This is what we call a spike raster. So each row there represents one channel of recording, and time goes from left to right.
Doesn't that look like
and each of those little tick marks is the time of a single
like
spike in action potential. All right, so presumably there's some information somewhere in there. How do we get at it? What are we going to do with it? Well, for the first application, which Max told you about, which is allowing paralyzed individuals to be able to control a computer, what we want to do is we want to reach into primary motor cortex and record the activity that's happening there. Primary motor cortex is the part of the brain that sends signals down the spinal cord and to the muscles to drive movement. Of course, it does that with action potentials. And in particular, we want to record from the hand and arm portions of primary motor cortex. So imagine that you have a person sitting holding a mouse, and they're sitting still, and then they make an outward movement with their mouse, and then they reach back. What would you see in the brain? Well, here's a synthetic neuron. I made these data up, but it gives you the idea. Here's a synthetic neuron that shows that in the background activity, when the person's at rest, maybe there's some firing. But when that person reaches outward, that neuron starts to fire a lot. And when he reaches back, the neuron becomes quiet. So this is what we call a neuron that's tuned to a particular direction of movement. Now, maybe we'll record from another neuron, and this neuron may have a different pattern. It may be tuned to the return movement and not to the outward movement, so it fires more on the return. What if we ask the person to do that movement again? What we would see is a similar pattern of activation. So the neuron on top still fires more for outward movement, and the neuron on the bottom still fires more for the return movement. But you'll notice that the patterns are different. And that's because neural activity in the brain is random. It has stochasticity, which means that even though the person may be intending to do the exact same thing from one movement to the next, the neural code, the neural representation at the level of an individual neuron is noisy. And this is just one of the reasons why we need to record from lots of neurons in order to be able to gain a high fidelity readout of what the intention is.
That makes
so let's say we record from a bunch of neurons. It might look something like this. Now, if you look at that, you might think that looks pretty messy and it's not clear what's going on. But I'm going to do a little trick. I'm going to take those neurons and I'm going to rearrange them so that they're in the order of the tuning that they have, just as I told you about those two neurons. And if you do that, look what happens. Now suddenly structure emerges. And I think you'll agree, looking at that there's information in that stack of neurons that tells you about the movement. And that's exactly what we want to do. We want to do that kind of magic in an automated way to read out the movement.
What?
The way we do that is by building something that we call decoding algorithms. These are mathematical algorithms that we tune based on data like these to be able to take in just those rasters of spiking activity and output the movement that the person wants to make. Okay, so for these little fake data, I built a very, very simple decoder, and sure enough, it's able to capture the intended movement. This is what we want to do on a bigger scale. Now, you might say to yourself, I don't understand, you're talking about moving, but I thought it was about paralyzed people, right? So how does that work? Well, it turns out we know from a lot of prior research that even if you're not actually making the movement, even if you're just thinking about the movement, or even if you're watching someone else make movement, the cells in motor cortex respond in a similar way. So we can build up these decoding algorithms just from those kind of data. And then a paralyzed person can think about moving the mouse, and the cursor will move. Now, this kind of decoding has been done in a fair number of academic labs, including my own before I came here, and in humans in academic studies. What we want, what Neuralink's goal, though, is to be able to do this with a clinical device that people can take home and use on their own, and that has orders of magnitude more channels, orders of magnitude more neurons that we're recording from. With that, we think that people will be able to get naturalistic control over the computers, not just a mouse, but also a keyboard, game controllers, and potentially other devices. That's what we're trying to do. Now, I've told you about the arm and hand area of motor cortex, but the devices that we're talking about, because of their high bandwidth and the ability to tailor the location of each individual electrode to a person's individualized cortical anatomy, we should be able to reach anywhere in motor cortex. So, for example, there are areas at the base of motor cortex that are responsible for driving activation of the speech articulators. There was a recent lovely study from UCSF that showed that from activity like that, you can actually decode speech. So you can decode the movement of the articulators, and from that, you can create synthetic speech. So potentially, with a device like this, you could restore speech to a paralyzed person who's no longer able to talk.
What?
But there's no reason in principle that we can't reach all of motor cortex. And that would give us access to any movement that a person thinks about, any movement at all. A person could imagine running or dancing or even kung fu, and we would be able to decode that signal. So that could give a paralyzed person the ability to control, say, for example, a 3D avatar that they could use for online gaming or sports. It could allow them to control a wide range of assistive robotic devices.
Yeah, or them.
And ultimately,
they could learn kung fu.
if and when the technology for spinal cord, nerve,
the moving.
or muscle stimulation gets far enough, ultimately, it could be used to restore that individual's control of their own body.
That's crazy.
Okay. And I've talked about readout, but remember we want bidirectional information. We don't only want to read information out of the brain, we want to be able to put it back into the brain. Now to some of you that may seem a little bit fantastical that you could write information into the brain, but actually the basic building blocks of that technology are already there. This is the same image that you saw before of an electrode next to a cell. It turns out if you pass a tiny amount of current through that electrode, what happens is that you activate cells nearby. What? You cause them to fire an action potential, one or many. And that is the technology that is already being used widely outside the brain, say, for example, for cochlear implants, which have been used for decades to restore hearing to the deaf, and more recently, in the eye, to restore vision to the blind in a fairly rudimentary way, as I'll tell you more later. But in addition, you can use the same technology in the brain, for example, to restore the sense of touch or to restore vision. And I'm going to tell you very briefly about those two applications. So let's start with the sense of touch. Consider this little bit of tissue of brain that I've just highlighted here that's at the border between motor and somatosensory cortex. So if we blow that up, what you can see is that somatosensory cortex has a very special property. It has what we refer to as a spatial map. And what I mean by that is that there are regions that encode the palm of the hand and each of the 5 digits, for example. So if we were to stimulate at one little location, say in the thumb part of the cortex, the person would feel a sense of touch or pressure on their thumb. Or if we were to stimulate 2 sites in the palm area of cortex, you might feel a couple of points or touches on your hand. This kind of technology has been demonstrated in many academic labs. And in a recent really nice paper, it was shown that with subjects controlling a robot arm through BMI, getting tactile feedback of when that arm or when the hand of that arm was grasping an object improved the ability to pick up and place objects with the robot. So this is the kind of thing that can really help decoding. So imagine what we could do if we were able to take our device and cover all of somatosensory cortex. We could give rich sensation of objects, of haptic feedback when you're manipulating objects. We could maybe feel different textures. But it's not just about improving the user experience. It's also about getting to the level of functionality that we want. Imagine for a second, imagine typing. Now imagine typing with your fingers anesthetized. That's going to be pretty hard.
Yeah, true.
So that haptic feedback, that sense of sensory feedback during movement is going to be important going forward. And yeah, okay. So that sensory feedback for the hand, we can also potentially provide visual feedback. So visual cortex, just like somatosensory cortex, has maps. So there's a spatial map in visual cortex, which is here in orange in the back of the brain. So for example, if we stimulate a particular point in cortex, we might see a flash of light in a little punctate spot in front of us. And this was demonstrated many years ago by neurosurgeons, and it's been used in academic labs, and that we call that little dot a phosphene. And if you stimulate another area, you'll get a phosphene in a different location.
What?
So the idea here is that you could stimulate a bunch of different areas, and you could create kind of like a dot matrix image of the visual world, which could provide a rudimentary form of vision. And there are academic labs and even companies that are working on technology just like this.
That's crazy.
But there isn't just one map in visual cortex. Actually, there are a bunch of different maps. This is a good example of how the brain works. There's a spatial map, but there are also maps telling you about the orientation of edges in the field. There are maps telling you about color. There are maps telling you about the size and speed of objects moving. So what we want is a device that has sensors that are small enough, electrodes that are small enough, and a high enough density that we can tap into that rich collection of maps with our stimulation devices so that we can do better than just dot matrix, so that we can actually create rich visual feedback for the blind. That's the long-term goal. Okay, That's just, again, one more example of the way that these devices can be used.
Bro, you can control a whole person.
So I've talked about
You could just
recording
completely
signals, and I've talked about stimulating.
whatever you wanted.
You can combine those two to treat a variety of neurological disorders. Max talked earlier about deep brain stimulation to treat, say, for example, Parkinson's disease. And many people have those devices in. Academic labs have recently shown that you can do better with stimulation, you can treat better, if you also are able to record the state of the brain, say from motor cortex, and use that to shape the pattern of stimulation.
Makes sense.
Deep brain stimulation, or DBS, has also been used for dystonia. It is already approved for dystonia and obsessive compulsive disorder. And we think, again, closed-loop therapies can do better. And in fact, for epilepsy, there's already a commercial product that does this kind of closed-loop seizure detection and disruption, although it does it with only about 8 electrodes.
That's weird.
There are many other diseases. Oh, no. All right. We'll get there. Sorry. There are a number of other neurological disorders where DBS has promise, but is still an investigational stage, like depression, chronic pain, tinnitus. Now, even though these diseases are currently being treated with these big DBS electrodes like you've seen, we think that there's a potential here for the kinds of devices we're designing to get individualized, highly focused treatment that will reach broader patient populations and be able to be more effective in the way that they treat these disorders.
It's badass.
All right, lastly, I want to tell you about not just sensory input and motor output, but about thought. So there are parts of the brain where we know that there's neural activity that encodes the things that you're thinking about. And one great example is an area called the hippocampus. The hippocampus is involved in memory formation, and it helps store episodic memory, things that you remember from your life. It also has a particular kind of memory for locations and views that you know. For example, it'll have cells that represent places in your own home or in a city that you know well.
Damn.
So imagine that you could record from a collection of neurons in the hippocampus of somebody who lived in San Francisco and knew it well. Then it's likely that they would have some neurons there in the hippocampus that represent various locations in Golden Gate Park. And so if that person were to take a car ride, for example, from the ocean through the park, you would see those neurons fire in order as they took that ride. First a neuron that maybe represents a view of the ocean, and then the bison in their paddock, and so on.
That's crazy.
All right. So
What?
I've told you about the way that the brain represents information, and that these sorts of encoding methods, representations in the brain, are things that we can learn to decode. And I've told you about some of the applications and how they might work. As the device technology gets better and better, and as we get more and more experience with those devices, we and other researchers will be able to bootstrap off of those advances to reach other brain areas and other applications. That's what we're trying to do. Neuralink's goal is, neuroscience has shown that a wide variety of information content is readily available in the brain. We know, for example, that there are signals that encode speech and language. There are signals that encode your mood. There are signals that encode the sense of pain, when you're hungry and when you're thirsty. There are signals that encode your memories, and even esoteric things like mathematical reasoning.
Oh, shit.
What Neuralink wants to do is to give people the ability to tap into those representations, to get better access to that information, both to repair broken brain circuits and also to ultimately give us better access to better connections to the world, to each other, and to ourselves. Thank you.
Damn.
All right, thanks. So we're going to take a risk here and just do some Q&A. That hopefully was a good understanding of the brain. For nice work, guys. It's like that's very proud of the Neuralink team. They've done amazing work, and yeah, it's a really smart group. There's a lot more there's a lot more really smart people. So what you're seeing here is the outcome of a lot of hard work by the Neuralink team, yeah, I think there's some pretty impressive stuff. So we can take some more questions from the audience. The lights are bright, so you might have to just take you later or something.
Yeah. Is there a roadmap towards allowing people or organizations to actually push custom code to these devices?
This is a really interesting question. So it's definitely too early to really think about this. Elon, I don't.
I think we'll hold up on the custom code immediately. Yeah. But I think it's conceivably there could be some kind of app store thing in the future, or some sort of platform with like a very rigorous verification of the application. Yeah, but yeah, I think that this is certainly not meant to be sort of a closed system. Ultimately, if we can enable others to contribute, whether they're at Neuralink or not, that would be a good thing, for sure.
And just add one more thing to this. We've had some discussions, like it might be that if you want to build an app or a business on top of a brain-enabled API, then your business model can't be advertising, for example. It's very important to us that this is that this turns out well for everyone, and so there's thinking like that going on.
Yeah. Sure.
Does the brain's neuroplasticity make this harder or easier for you guys? Like, are you trying to interpret a continually moving target, or is there a chance for
We can't hear his question.
symbiosis once the brain realizes what's happening to it?
Yeah, there's no doubt that plasticity will make things. So the question was whether neuroplasticity will help or hurt our effort, and I think there's no doubt that it will help. First of all, there's just the fact that you have to learn how to use these devices. But for example, in work that we did in my lab earlier, we showed that you can write in information that isn't perfect. It doesn't get that map perfect. Or even it can be somewhat quite different from the map. But ultimately, you can learn to use that through plasticity. And there's going to be a lot of learning required, and the ability of the brain to adapt to new information, and in particular, the ability of the brain to take information that comes from multiple sources and merge it in an effective way is, I think, the kind of thing that really will facilitate complex new tasks with these devices.
I mean, it stands to reason that the neurons are responding to electrical pulses. So the electrode is providing electrical pulses, to the neuron, an electrical pulse is a neuron. It just thinks it's a neuron, and it's going to, for sure, adapt dynamically because it just sees electrical pulses, and it's going to respond to those. Yeah. So, yeah.
So there's no advertising.
I mean, Jesus. I mean, you'd have really no escape. We cannot do that. That would be an ethical barrier. Yeah, so the question is, if this will not be advertising driven, which I think would be unwise, then how will it be paid for, essentially? Is that correct? Or how will we ensure that it's broadly available?
Yeah.
I think that the cost of these brain disease or brain injuries is extremely high to society. If you have to take care of somebody, or if they need comprehensive medical care or hospice, this is actually very, very costly to society. So I think the economics of solving for that make a ton of sense. And if you enable somebody to work and be productive, contribute to the economy, I think that will. I think that the economics of that will easily pay for itself. And then, in the limit, of course, if you want to be symbiotic with AI, it'd be like, I think it's safe to say you could repay the loan with superhuman intelligence. I think it's a safe bet. So I think the economics of this will work out. And the first order is really just to make sure that it works and works safely. And then I think it'll really be the option of the person. But it is critical that this be sort of, as we've talked about before, like a LASIK-like device. If this has to be done by a neurosurgeon, it cannot be scaled. There just aren't enough neurosurgeons.
Makes sense.
So it must be just as one wouldn't want sort of like a hand operated laser for an ophthalmology situation. You really want the robot doing it with precision. The same thing goes for the brain interface. So, yeah.
Interesting, super interesting. Ike, follow, share
Sure.
if you can.
Yeah, so the question is,
Elon.
have we implanted the chip in animals? And if so, what are the results? So I think first it's important to say that we regard any chip implant, even if it's in a rat, as a very serious thing. Like, so we even care about rats, even though they have the Black Plague and everything, So like they arguably have some karmic payback. But nonetheless, we care about rats. So, and then we're extremely sensitive with monkeys, and we work with the University of California at Davis for any of the monkey activity. So, and the results have been very positive. Do you want to maybe talk about? I know this is a sensitive subject.
Yeah.
But I think it is. Yeah. We definitely need to address the elephant in the room, the monkey in the room.
Yeah, I mean, I think that there's.
He's worried about animal rights activists.
We wish that we didn't have to work with animals, right? That we just wish that wasn't like a step in the process, but it is. It's a very important part in the research and development process to produce better outcomes for human patients and improvements in human health. And we try to be very thoughtful and we follow the 3 R's of like reduction, replacement, and refinement of laboratory animal medicine, and we try to be very careful and thoughtful about it and do it as efficiently as possible, because we believe that the benefit to humanity is in the end like the benefits outweigh the negatives.
The questioner also asked about the results, and there is a paper available, I think now, soon, that has some of the results in them.
Okay. I'm gonna check that out.
Yeah, I mean, but we have made a monkey has been able to control the computer with its brain. Just FYI.
I didn't realize we were running that result today, but there it goes.
He said a monkey knows how to control a computer,
The monkey's gonna come out of the bag. So, this is much good for a fun point of it. Yeah.
He said the monkey knows how to control a computer. Bro.
Can we speak about the FDA path that we want to pursue and how we might work with the scientific community? You guys want to talk about it?
Yeah, sure. Why don't we start with FDA?
Well, I was also going to say, we're under no illusion that we think we can do all of the science required for this ourselves. There's an immense amount of neuroscience to be done with these devices, and there's a huge amount that we have to learn about the brain, and that's going to be a much larger thing than just Neuralink. And we want to get these tools into the hands, eventually at the right time. I think that we're still a very small company just focused on getting our first patients, and we have to be laser focused on that. But we want this to be a thing that is much larger. We want this to be a field, right? We want this to really fuel advancement of the field. Because the most important thing is not that Neuralink is this one specific place, but that it advances all of us. And for the FDA, there's a pathway. We're pursuing an early feasibility study, IDE, and it's and there's the FDA actually put out draft guidance in February that's very specific to the type of thing we're doing, and it's pretty prescriptive. It's a checklist of what they want to see, and there's a lot in it. You have to show that it's going to be expected to be safe and biocompatible and stable, but you work through that and you give them the documentation.
But I mean, people in academia right now are quite constrained in working with the Utah arrays. That's the most advanced thing in academia. And our system is at least 100, arguably 1,000 times, well, on the order of 100, I suppose, relative to the potential of the Utah array, 2 orders of magnitude improvement at the experimental level. So I think it probably would make sense for us to make more of the robots and provide the chips to academia to further the science. Sure. Sorry, okay. It's hard for me to see.
So you've obviously been working under the radar for quite some time, and you've made significant advances. Now that you're public and very obviously recruiting today, and I would assume looking for additional academic partnerships to sort of accelerate your development, what is the best way for academics to get in touch with you and start to create these new collaborations and advance mutually on the side of academia and the side of Neuralink?
Sure. What is the best way for academics to get in touch with us to collaborate on furthering the field and N1? Yeah. What do you guys think?
So, first, if anybody out there has technologies or ideas that they haven't heard us talk about today and that they think could be useful for us, they should reach out and tell us about it. We're always interested in new technology and new things that are happening in the field. So that's a first. As far as getting the academic community access to data, for example, this is something that we are committed to doing. The details of the pathway on that aren't fully worked out. There are a number of options. And to be honest, if you have ideas about ways that anyone in the academic community thinks that it would be good to engage with us, we're willing to listen. And we'll pick one or two, and we will make it possible for the technology that we're working on to have a very broad impact on the field. That's definitely one of our goals.
Yeah, I mean, the things that sort of really drive the technology are, advancing the chip design, the software on chip and for interpretation of the results, material science especially for the coatings of the electrodes, like how do you have a long life electrode. It's quite a difficult thing to get that coating, get the materials right, and then the application of the materials for the something that you want to be, because you want these electrodes to last for many decades in the brain, but this is quite a difficult environment. It really wants to corrode. So getting the right coatings is incredibly difficult. It's a tough material science problem. Sure.
On that note, you pushed quite a bit on the material science and then hermetic packaging. Do you guys have a sense? It's only been doing it for 2 years and things are changing, but do you have a sense of the longevity? Is it outperforming, or do you consider it a solved problem compared to rigid Utah arrays?
Right. Do we consider the longevity a solved problem? Definitely not. So I think the longevity is one of the key questions, and it's difficult to say, like, until you actually have it implanted, how long does it last? And then if it does start failing, does it fail in a benign way or in a bad way?
Yeah, exactly.
So
does it go crazy?
I think there's not enough time yet to actually say whether it is going to live for a long time. It obviously makes sense to have accelerated live testing of the electrodes, so in a non-brain situation. So you figure out something that's actually a worse environment than the brain, and which is actually quite a difficult environment for a chip. And electrodes. Find something that's even worse and have accelerated live testing. That's one of the key things. And then they need to confirm that in an actual brain. So, I mean, the latest results are quite promising, but it's too early to reach conclusions. I think we've just recently seen what we think is a remarkable breakthrough, but time will tell.
Damn.
Sure. Yeah, I can just.
I was wondering, how are you planning to avoid the mechanical mismatch between the neural program, the brain, and that to make probes?
How will we address the mechanical mismatch of the electrodes and the brain? Essentially, because the cells are like jello and electrodes are really hard. And so you have a big stiffness difference between brain cells and the metal electrode. Yeah, do you want to?
Ask a question.
You're on.
Oh, I'm on. Yeah, I mean, that's part of the reason, one of the reasons why we went towards flexible materials. Like, there are a lot of different kinds of probes out there right now, if you look it up. And that's the main purpose of going flexible and also going smaller. So as I said, that we're really trying to make it as invisible to the brain as possible. And then on top of that, as was mentioned, coatings. So all of those combined, we're hoping to significantly decrease that immune response.
But essentially, if you have something with high modulus and something with low modulus, but if you make the high modulus thing very thin, it becomes quite flexible. Yeah.
That makes sense.
Moment of inertia. So I'll try to answer a question at the back there. It's hard for me to see behind the camera.
Oh my God! Mess up a petition with something that's just. Oh God. They'd have to get it like 2 microns or. Harry, what is that? I don't even know.
So I think if summarize the question, like essentially, do we look at like higher order feedback where it's sort of at the maybe whole limb level or combination of limbs or a whole word or letter as opposed to an individual phosphine or something like that? Okay.
Yeah, I think that, of course, that's a stimulation result, not a recording result. And it may have something to do with the kind of low resolution of the stimulus, that the psychophysics of that, it's hard to perceive it as a complete letter, but you get filling in of motion that helps you perceive the object. That's kind of sort of my thinking of what's going on. And so, I think these are the kinds of questions that honestly we haven't yet addressed. When I talked about visual stimulation and the kind of rich visual stimulation that we want to, just to be clear, that was aspirational. And so, come back and ask us in a little bit, and I'll answer.
Yeah, but there are, there are like individual neurons that you can trace to particular names and concepts and people, at kind of advanced long-term level, I think people would have kind of like if two people had a Neuralink, you'd be able to effectively have a sort of really high bandwidth telepathy, or actually technically going over radio waves, but you could actually communicate at a sort of complex meme structure level, using the Dawkins version of the meme. So then you could really have like potentially a new kind of communication. It's sort of a conceptual telepathy, essentially.
Wow.
It would also be consensual. I'll try to answer something in the back. Yeah, I can hardly see you, but anyone in the back there, basically. If you talk.
Yeah. Firstly, I'd like to congratulate you guys on the technology that you've created, all the accomplishments.
Thanks. Great team.
So, I apologize for keeping this out of the tech atmosphere, but more into the philosophical realm. I'd like to know, essentially, the implications of Neuralink is to solve a lot of the problems that humans face on a day-to-day basis. In Parkinson's, it's like 7 to 10 million people worldwide face it. I wrote it down. So, I understand that, humans under
Wonder what the fuck she's talking about.
to find great meaning, and to find meaning in life. And I wanted to know if Neuralink, if their ultimate goal is to eliminate suffering. If so,
I can't even hear her. Can anybody else hear the question? I can't hear what she's saying.
faced with, how are we?
Hopefully Elon's got this.
I have like a crude
Haha.
answer.
Oh, okay. What's your answer to what do you think we should do? I mean, we're open to ideas here. The overarching objective is to make the future better, aspirationally, and to hopefully not pave the road to hell with good intentions. Because I think the road to hell is mostly paved with bad intentions, though.
I mean, my answer is very, very, very crude.
Okay.
But essentially, this technology has never surfaced the face of the earth, so that right now it's like looking into
big question.
Yeah, I think
This
that
dude
it's a
this
it's a
dude
big
on the
philosophical
end
question.
Right here. Looks like he needs a chair. He's like,
What will? It's hard to say what the future will be with something like this brain-machine interface. I doubt that we would be able to eliminate all suffering, and it actually may be ultimately oddly dystopian if we do eliminate all suffering. That actually may not be a true utopia. There's like generally like stories about utopia tend to turn into dystopia. So I think we can definitely make a significant difference, and we can address. When I say we, I mean humanity can address a lot of the suffering that occurs in the world and make things a lot better. And I think a lot of times people are quite sort of negative about the present and about the future, but really I think if you're a student of history, when else would you really want to be alive? Now's the best time, pretty much.
Yeah, straight up.
Yeah. It's like those who think the past is better have not read enough history. Okay, way in the back there, I see actually can see a hand. Yeah.
Can you talk a bit about the computational backend that derives gain from these reported pulse streams? Is it like traditional compute, a bunch of GPUs, a bunch of asynchronous FPGAs? Does it run on AWS? Is it
Yeah.
Yeah, guys.
Yeah, I think that DJ should answer some of this, but
so
yeah.
No.
No.
It doesn't run on AWS.
I'll also say that you often have very tight latency constraints in this system.
Yeah, exactly.
You really have to run locally.
Yeah, so the question is, how are we doing the back-end computation? What are some of the methods that we're doing it? Yeah, so as Max just mentioned, latency is something that we do want to minimize as much as possible, especially in the context of doing closed-loop BMI, so being able to record and also stimulate and put information back into the brain. So in order to make sure that that latency between the end-to-end system is minimized, we need to have all of that computation locally. So that's one instance of the evidence of spike detection that you saw that's slowly progressed from computation from the computer onto the integrated chip is something that we strive to do as well with closed-loop BMI algorithms.
Yeah, I mean, essentially the vast amount of the computation is actually done locally on an ASIC, effectively. So the amount of data that needs to be communicated beyond the body or the brain is really distilled down to a small amount. And as DJ was saying, like especially important for if you want to say give someone who's a tetraplegic the ability to type at 40 words a minute, which is one of our goals, and that requires a very low latency feedback loop.
That's badass, though.
I think
you could just sit there and
okay, last question. Okay, go. Yeah, fire away.
In terms of the vision of the company, are you trying to get to the stage where you can have one thread per neuron? And if not, what kind of number?
That's a good question.
And at what order of magnitude of channels would you consider trying it yourself?
Okay, this is a few questions packed in there. One of the first question was, essentially to summarize what we're saying is like, what's the ratio of electrodes to neurons? Because you wouldn't want a 1-to-1 ratio because that's a lot of electrodes. So you really want to actually have that ratio be as big as possible, and ideally at least 100-to-1, maybe 1,000-to-1, ideally. Because the bigger the ratio of neurons to electrodes, the fewer implantations. It's going to be just way better. For sure, you'd want to read a whole bunch of neurons and then be able to stimulate neurons or a cluster of neurons by varying the field potential, so that you don't need to have a 1-to-1 stim or read ratio. Ideally, 100-to-1. You guys want to add?
Yeah. I guess I would
or more. Yeah.
I think it's important to add to that any answer we give to what's the right number of electrodes at this point is speculation.
Yeah.
That's part of the. I mean,
speculate.
Yeah, but the point I'm trying to make though is that this bootstrapping that we anticipate is going to happen. We're going to put in devices, they're going to be lower level. From that, we'll be able to find out the information content and information density in the areas that we're looking at with the electrodes we have. and we'll be able to bootstrap up from that. So, you know, I actually believe that we are the ones that are going to be able to answer that question without speculation.
And I'll say, when you look at the anatomy of the brain is mostly silent. Like on average, a classic electrode can see somewhere between 0 and 4 neurons electrically by different waveform templates. But when you just look at the anatomy and like the distances, you'd expect it to see more like 1,000. And so this question of why is the brain so silent is an interesting one. And one of the hypotheses is that there have a lot of neurons that have very narrow receptive fields that only fire when they have very high information content updates with respect to something specific. And one of the challenges with spike sorting is that you can't tell, you can't tell apart like another spike of a neuron that you think you're recording from with, that was the first time I heard from that neuron specifically that I don't know is there, right? And as you have these long-lasting chronic devices, you'll be able to get more of that out in the decoding.
I'm watching Elon Musk and their Neuralink.
Yeah, I mean,
they're basically
I think it's going to vary. The electrode to neuron density is going to vary quite a bit depending upon what part of the brain it is as well.
That's cool.
If it's sort of somatosensory is probably like a pretty big ratio. And you can get pretty impressive results like controlling, essentially a cursor with your brain.
They did.
You don't need very many electrodes for that. So, and there's a lot of neurons in the sort of motor cortex. So, I think there's some cases where you could have, I don't know. This is really speculation, of course. I mean, some places where you could have maybe 10,000 to 1, and some places where you'd want maybe 10 to 1. It could probably, I suspect it will vary quite a bit.
And I just really quickly, I think Dan's question, because this is longevity is a really important question that we think about all the time. I don't think that we're releasing histology in the paper today, but I think that just to put some pressure on this team, I think that we're running that around SFN probably. There's some really cool stuff in progress.
All right, thanks everyone for coming. Thank you. Great questions.
But I appreciate you guys. Hopefully I can give you a little bit of free advertisement, fair use or whatever it's called. But thank you. This was the commentary of the Neuralink update from Elon Musk. I hope you guys enjoyed it. Hit me up. Oh, I'll be on in a minute for GTA.